Hello and welcome to Lecture 1, Part 4. I'm John Steele, and this is Introduction to Robotics. In this segment, we're going to talk about DC motors and learn some of the fundamental principles that make them operate and look at a couple of their most important characteristics in preparation for doing some experiments and tests in the lab. So I hope you will develop an understanding of these fundamental ideas, particularly motor torque and motor power for DC motors, and you'll have an idea of what the challenge will be when you go to the lab and start testing them. So here we go. So as I said in the other segment, robotics is largely using DC motors. There are some AC technologies that are coming along, but I'm going to focus this course and these activities on DC motors because they are, by and large, the motors that are used in robotics. One of their fundamental characteristics is this ability to command speed by controlling the voltage and current that are going to those motors. So that is why we use them. Speed control is where it's at for robotics. So in the picture that you see on this slide, there are the pieces of a motor. There's the rotor, that is the part that rotates, and there you see the curled arrow to indicate that. In this case, the rotor and the armature are the same. The armature is the part that actually is energizing the motor system, and so that they are one and the same in this case. And then you see the blue and red partial rings, and those are the two sets of magnetic fields that are what the electric field from the armature is interacting with. If you look closely, you'll see like a cyan and a yellow set of bars that come up and touch the rotor, and those are brushes, and the copper-looking part that shows a break in it on the rotor, that is called the commutator, and it's actually that separation in the connection to the windings that changes every time the rotor rotates that makes the DC motor rotate. And we'll come back to that in the next lecture when we talk about DC motors more. Underneath that is the fundamental equation for the electromotive force of a DC motor, and basically it says that it's a cross product of the current flowing through the armature windings and the B field, which is generated by the battery. And again, we're going to talk about that more in the next lecture, but that's the fundamental idea. So in this slide, there are some pictures of a variety of different DC motors, from really pretty small ones, although these aren't the smallest out there, but fairly small ones up to some fairly large ones, somewhat large ones. And in fact, we're going to use one similar to those, I'll call them pancake-shaped ones sitting in the middle. Those are actually very much like the DC motors that come in the Lego kit that you get when you check it out. So basically, DC motors are small, sometimes relatively small. They're inexpensive. For example, small means the vibrators, vibrations you feel in your cell phone are being generated most likely by a little DC motor inside the housing of your phone. At least that's traditionally how it's done. And then there are brush and brushless DC motors. In this talk, we're going to talk strictly about brush DC motors, but brushless technology is really coming along, and there are lots of advantages to it, as we'll see later. So the current flows through the windings and creates a magnetic field that reacts against the magnetic field of the permanent magnets, and it's the interaction of those two fields that creates the force which causes the armature to turn, and it's the turning of the armature that gives us the mechanical energy that we use as the output from the motor. And many of you already know, for example, that a motor and a generator are really the same thing. It just depends on which is the input and which is the output. But we'll come back to that as well. So another important idea is to think about efficiency, and we'll look at this in more detail later. But basically, as you know, efficiency is output over input, and for toy motors, a typical efficiency might be 50%, whereas industrial grade motors, it's going to be in the 90%. So the amount of power you put in, you're going to get 90% of that out in terms of power for an industrial motor. Okay, so these are some of the fundamental torque equations. You recall from physics that torque is equal to R cross F, and in addition, for DC motors, the torque produced by the motor is directly proportional to the current flowing through the windings, since that defines the electromotive force. So we will see that it is the case that the demand for current will go up as the demand for torque in the motor goes up. And the units, as you probably already know, are things like ounce inches or Newton centimeters, or in some cases millinewton meters. Newton millimeters and millinewton meters are really the same unit. So, as it says, DC motor torque is proportional to current, and so we need to be able to supply that current in order to produce the torque we want. Now, you will also recall from physics that work is equal to a force through a distance. If you pick up a load of books and lift it, and it weighs 10 pounds, and you lift it a foot, then you've got 10 foot-pounds of work. And that's also the case that when you rotate a torque through an angle, that is also work. So torque T times d theta produces work. You also remember, I think, that power is the time rate of change of work, or time rate of change of energy. Remember that the change in energy is equal to the work done. So we can write power as force times velocity. We can also write power as torque times angular velocity. And in terms of the input to the system, since it's an electrical input energy, it's volts times amps. So the efficiency, as you may have already thought to yourself, will be the torque times angular velocity divided by the voltage times amps, which is the output over input. So I want to show you this graph, and what you see here is the theoretical, although they also, as you will find, they're pretty darn close to the reality. Relationships. In particular, look first at the red line, and this is referred to as the speed-torque curve. Speed as a function of torque. Torque is on the x-axis, and speed is on the y-axis. And so what happens is that as the torque, load torque, is changed as seen by the motor, its speed changes. So if we go over to the zero torque point, that is 0 on the x-axis, then what we notice is that we are at 1, this is normalized, but 1 unit of speed on the y-axis, and that's referred to as no load speed. So with no load on the motor, it will spin at whatever speed it's capable of. On the other hand, if we grab hold of that motor and make it stop turning, then it's experiencing a torque, a load torque, sufficient for it to stall, as we say. And that's the point down on the x-axis where torque is equal to 1 and velocity is equal to 0. Now, we'll see how this converts into power, but if you think about it, if you have a relationship from the previous where power is equal to torque times angular velocity, if torque is 0, then you have 0 power. If angular velocity is 0, you have 0 power. And so, sure enough, the torque power torque curve, that is, power as a function of torque, is shown here in blue, and it's 0 at both ends, but peaks in the middle. So it's a second order relationship. And as noted there at the bottom, you will see that the peak power theoretically occurs right at 50% of no load speed and 50% of stall torque. So that relationship is symmetrical. Okay, so let's talk about how you're going to measure these quantities for your DC motors, that is the Lego motors in your kit. So here's a cartoon that just shows a DC motor with a pulley or sheave, and sometimes called a drum. It's a drum when it's used to wrap up a wire cable, say on a crane or in an elevator. And in our case, we're going to build a structure to support the DC motor and build a gear train to offload the direct loading weight away from the motor, and we'll get to that in lab. But here's again the cartoon that shows the line being wrapped up on the pulley, and so we'll have a weight, and that weight is represented by a number of washers in a cup, and as you vary the amount of weight, then the time it takes to lift through some distance h is going to change, and I'll let you figure out the details of that, but basically you're able to measure the torque, and you're able to measure the power. And the question in the lab is, what are the speed torque and power torque characteristics of your DC motors? So that's what you're going to be doing in lab, and that's the end of this program. So the next things you'll hear from me will be actually lecture number 2, and talking about more details on DC motors and how they work. Hope you enjoyed it. Thanks. Bye.